Welcome to The Explainer. Today we're going to crack the code on one of the toughest puzzles out there in business, scheduling. We're talking about how to bring order to what can feel like total, absolute chaos. So think about it for a second. What could a custom car shop, a Hollywood special effects studio, and a hospital ER possibly have in common? Well, it might seem like a random mix, but they all face the exact same chaotic challenge. Every job that comes through the door is unique, and the workflow is completely, utterly unpredictable.
In the world of operations, this kind of environment has a name. It's called a job shop. And it is the polar opposite of a nice, neat, predictable assembly line. In a job shop, variety and unpredictability, well, they aren't the exception, they're the rule. And that, right there, is where all the trouble begins. As this quote puts it, the whole place quickly becomes a logistical nightmare. A job finishes up at one station, only to get stuck in line waiting for the next one, and at the same time, some other machine might be sitting totally idle just waiting for work. You end up in this constant battle of queues, bottlenecks, and just wasted time. So here's the puzzle. How in the world do you sequence all of these unique jobs to get the best possible outcome? And you know, best can mean a lot of different things. Are you trying to get everything done as fast as humanly possible? Or is it more important to make sure you hit every single deadline? These goals are often fighting against each other, and that's what makes scheduling so incredibly tricky.
You know, with any big, messy puzzle, the best way to start is to simplify. So let's look for our first clue by solving the simplest version of the problem. Lots of different jobs, but only one single machine, one resource to do all the work.
Okay, so our gut instinct, our human sense of what's fair, tells us to just handle things on a first-come, first-served basis, right? Seems obvious. But when your goal is making the entire system as efficient as possible, a different rule, one that's a lot less intuitive, turns out to be way, way more powerful.
And that rule is called the Shortest Processing Time Rule, or SPT for short. And really, the name says it all. You just look at all the jobs you have waiting and you pick the absolute quickest one to do next. Simple as that.
All right, let's get our hands dirty with a real example. Imagine you're standing in front of that one machine and you've got these 8 different jobs waiting. Each one has its own processing time, you know how long it takes, and a specific due date. Right now, they're just a random jumble.
Now, applying the SPT rule is a beautiful, simple process. You just look at the list, find the job with the shortest time, and you put it next in line. Then you do it again with what's left, and again, until every job has its place in the sequence.
And just by following that simple logic, we take that random mess of jobs and turn it into this highly optimized sequence. We start with the shortest jobs first, that's jobs 4 and 8, which only take 3 hours each. And we work our way all the way up to the longest one, job 6, which takes a full 14 hours. And this is where you really see the magic. This graph shows you the number of jobs just sitting there, waiting in the system over time. With the SPT rule, we're knocking out those quick jobs first, so the total number of jobs in the queue just plummets. It drops much, much faster. This minimizes the average wait time for everybody and cuts down on the amount of work just sitting around.
So here's the absolute key takeaway. The best rule depends entirely on what you're trying to achieve. If you look at this table, SAPT gives us the fastest average completion time, no question, just under 24 hours. But notice it results in 4 jobs being late. If your main goal is to minimize the number of late jobs, a totally different algorithm, like Hodgson's, is way better. It gets us down to only 2 late jobs, even though the average time is a bit slower. You have to pick the right tool for the job.
Okay, so we've got the one machine problem figured out. Now, let's up the ante a little bit and see what happens when we add a second machine to the puzzle.
So now the game changes. Every single job has to be processed on machine 1 first, and then it moves on to machine 2. This creates a whole new headache. Machine 2 can end up just sitting there, idle, twiddling its thumbs, waiting for machine 1 to finish its work. The goal is to find a sequence that minimizes that costly idle time.
Thankfully, a mathematician named S.M. Johnson gave us this really elegant algorithm that's basically a cheat code. It gives you the perfect solution every single time. And the logic is kind of wild, but it works. You find the single shortest task overall. If that task is on machine 1, you scheduled its job as early as possible. But if the shortest task is on machine 2, you schedule its job as late as possible. You repeat this, building the sequence from the outside.
And here you can see it in action. This chart shows the schedule over time. The top bar is machine 1, the bottom is machine 2. See those empty white spaces on the machine 2 bar? That's wasted money, it's idle time. But by applying Johnson's rule, we create a sequence that packs the jobs together as tightly as possible, minimizing those gaps and keeping the whole system humming along.
And the result is a real, measurable improvement.
the total time to finish all the jobs, that's a metric called the make span, drops from 47 hours all the way down to just 42. That's 5 hours saved, more than a 10% improvement just from sequencing the work intelligently.
Okay, so one machine, solved. Two machines in a row, solved. But what happens when we step into the real world where things get a whole lot more complex?
Because this is what a real job shop looks like. It's not some neat little flow from machine 1 to machine 2. No way. Job A might go from a lathe to a drill press, while job B goes from a grinder back to the lathe. Every single job has its own unique winding path.
And when that happens, the complexity just explodes. I mean, just look at this graph. It looks kind of nuts, right? This is what it takes to find the perfect, optimal schedule for just 2 jobs with unique routes. You have to find the shortest path from the bottom left corner to the top right without hitting any of the roadblocks. Now just try to imagine doing that for thousands of jobs. It becomes mathematically impossible to find the perfect answer.
So, if finding that one single perfect answer is basically impossible, what do managers do in the real world? Well, they don't give up. They turn to a toolkit of simple, effective rules of thumb.
These are called priority dispatching rules. They're basically simple heuristics that help a manager or a machine operator decide which job to grab next. We've already seen a few, like shortest processing time. Others add a little more nuance. For example, the slack rule tells you to prioritize the job with the least amount of wiggle room, the smallest gap between its due date and how long it takes. It's great for avoiding late orders. Each rule is just another tool in the manager's toolkit.
And that really is the heart of it all. This is how complex systems get managed in the real world. When you're facing that kind of overwhelming complexity, where a perfect solution is totally out of reach, you don't look for a single magical answer. You use simple, proven rules to bring a practical, effective sense of order to the chaos.
And that's why this stuff isn't just theory. It's fundamental to making everything run better, from that custom motorcycle shop to a hospital emergency room. So let me leave you with this puzzle. Think about an airline's maintenance crew. What's their most important scheduling goal? Is it overall speed? Is it hitting a hard deadline for takeoff? And based on that goal, what rule from the manager's rulebook would you use? That's the puzzle they have to solve every single day.